it. Um, I know this audience is very familiar with exoplanets as a topic, so I won't belabor the point too much here, but just to warm everybody up, we've seen amazing progress in the field since the discovery of the first extrasolar planet in 1995. And now, just a little over 25 years later, we have over 4,000 confirmed exoplanets. You can see the acceleration in the rate of discovery from this plot, showing the number of planets discovered every year. And we expect more planets still incoming from ongoing surveys like TESS and KAOPS, as well as future missions like Plato and ground-based surveys as well. If you boil all of these discoveries down into just a few numbers, we know that planets likely outnumber stars in the galaxy. So sun-like stars typically host at least 0.7 planets per star. And that's a lower limit because we haven't yet had the sensitivity to explore the outer regions that are farther away from these stars, or for the smallest types of planets that are below our detection sensitivity. M-dwarf stars, which are the smallest stars and also the most common in the galaxy, host even more planets, with an average of at least 2.5 planets per star. And as all of you know, the importance of this discovery was recognized by the Nobel Prize awarded to Didier Queloz and Michel Mayor just a couple years ago. What we've learned from these planets already is that they're much more diverse than the solar system. Here's a plot showing planet mass as a function of distance from host star. And this is not corrected for any type of selection effect, but it's just intended to illustrate the diversity of the systems that we have discovered. And so one really noticeable population of planets is very hot ones with short period orbits. The shortest known orbital periods are well under 24 hours. So these are really incredibly hot planets, which open up new and interesting pathways to characterizing them in detail. We've also found an abundant population of planets that are intermediate in size between the Earth and Neptune. These are debatable what the best term is for these super Earths, mini Neptunes. I'm actually preferential to another term, which I'll get to in a minute. We've seen planets that are on the boundary between what we would typically consider a planet versus a star, as well as a host of oddball things, high eccentricities, planets orbiting white dwarf stars or two stars, planets that are closely packed in their orbits or in orbital resonances. We've even seen some planets called superpuffs that have such low densities that their average density is comparable to cotton candy. And there's also a big part of this parameter space that we haven't yet had the sensitivity or time to explore, and this includes most of the solar system planets. So now that we've found all these planets, what do we do with them? Well, what I am most excited about is characterizing their atmospheres in detail. And by studying the atmospheres of planets, we can learn a lot about how they form, what they're made out of, how they evolve over time. We can even in some cases see that evolution in action for planets that are in the process of evaporating. That's something that we've seen. We also know that many of the planets that have been discovered are in very extreme environments that are quite different from the solar system. And so that includes planets on short period orbits that are tidally locked. So they have a permanent hot side and a permanent cold side. So what does that do to your climate, to your cloud formation, to your atmospheric composition on the day side versus the night side? And of course, finally, the huge question that motivates many of us, myself included, is whether we can infer the presence of life based on studying the present day atmosphere of another planet. Two really quick slides on how we actually do atmospheric characterization. And this is relevant for transiting systems where the planet periodically passes in front of and behind its host star. During a transit, the starlight will filter through the planet's atmosphere where it can be absorbed or scattered. And when the planet passes behind the star, any thermal emission or reflected light coming from the planet are blocked during that secondary eclipse. And based on these measurements, particularly if you have spectroscopy, so you can study how the size of the planet or the apparent brightness of the planet changes with wavelength, we can determine both the atmospheric composition, so what the dominant chemical species are in its atmosphere, as well as some information about the temperature and how that changes with altitude. And finally, we can also learn about any clouds or haze that are present in the atmosphere. This is intended for a bit more of a popular audience, but everybody really likes it, so I keep it in. This is what the Earth looks like from space. You can see the moon in the background and the beautiful blue Rayleigh scattering signature and optical wavelengths. If you move into the infrared, this is what Earth looks like. You see that Rayleigh scattering signature is gone. But if you move just 1 micron further red, you can see that the Earth looks a little bit bigger, and that's thanks to absorption by ozone. So if you toggle back and forth between these two pictures, you can see exactly the effect that we're searching for exoplanets. And I like this because it gives you like a real visceral sense of exactly how challenging this measurement is. We're starting to do this for Jupiter-sized planets and pushing really hard to get to Neptune-sized planets. But doing this for a true Earth analog is really, really, really challenging. So I won't show very much or really any other raw data in this talk, but I do think it's worth mentioning in at least one slide that exoplanet atmospheric characterization is really difficult. Here's an example of raw data from the Spitzer Space Telescope. That's the top panel. This is a phase curve observation of a hot Jupiter as it completes an entire orbit around its host star. And you can see all kinds of bumps and wiggles in there. There's a transit in the middle that's pretty obvious, but any other effects take a lot of care and very, very meticulous data analysis to tease out.
Sorry, Laura, before you move on, there was a question.
Yeah.
Why does the moon also look bigger in the radar image?
Say that one more time.
Why does the moon also look bigger in the radar image?
Does it? Oh, maybe a tiny bit. That's a good question. Maybe that's a data processing thing. I'm not sure. No one has ever noticed that before. Yeah, I don't have a good answer for you. I think there was some pretty elaborate post-processing done to get these images like this. Like if you notice really carefully, in principle, you ought to see the entire moon at this wavelength, and you don't. So there might have been some image processing that leads to that. Good eye, whoever asked that. All right, so speaking of image processing, if we do this for exoplanets, it's also difficult. And thanks to many grad student PhD theses worth of work, we're able to get from something that looks like the top panel to the bottom panel. I noted with the red arrows the typical size of these effects. So typical instrumental noise for Spitzer data is on the 1% level. This is correctable to 0.1% precision and even better. But to truly push to an Earth analog, you'd have to do orders of magnitude better than that. Exoplanet atmospheres are also really tough from the modeling standpoint. And the way I like to think about this is that the models have to cover a really large dynamic range. We care about effects that are happening on very small distance scales, so microphysical haze formation, for example, as well as planet-wide distance scales. So how does material circulate through the atmosphere? How does heat exchange happen between the day side of the planet and the night side of the planet? We also care about a wide range of timescales. So everything from very short timescales, that would be weather, to how how the atmosphere evolves over the entire lifetime of the system. So how much of the atmosphere can escape or erode over giga years. Is there another question in the chat? No. I can't actually, when I'm in screen sharing mode, I can't see the question. So just interrupt me if other stuff comes in. Okay, so a little bit about what I'm doing at the Max Planck Institute for Astronomy. As Eve mentioned, I am the founding director of a brand new department called APEX. This is us. This slide shows the entire department at the moment. We started just a little over a year ago. And the goal of APEX is to bring together experts in a really wide range of topics related to atmosphere characterization. So that includes observers, theorists, instrument builders. Eventually, I'd like to expand to lab science as well. And this is a really fantastic opportunity to have a bunch of experts together all in one place so that we can talk to each other and share ideas and work collaboratively. I do not, because we're so new, I don't have a lot of results to show you yet. So I hope you have me back in a year or two and I'll be able to share some of the work that our students have been working on. Okay, so the way I've structured the rest of the talk is that I'd like to walk through a couple of frontier questions that I'm really interested in answering. And I'll start with some classic results and then give an update about where we are now. So the first one I'd like to talk about is using the present day atmospheric composition of a gas giant planet as kind of a fossil record of how the planet formed. And the idea here is that for a gas giant like Jupiter or Saturn, the atmosphere was accreted from the protoplanetary disk and from gas and from solids, and the composition that we see today is a reflection of those initial disk conditions. And so as an observer, my questions are very, very basic. I'm interested in measuring the metallicity of the planet's atmospheres. There's a well-known trend in the solar system that the more massive the planet is, the less metal rich its atmosphere becomes. So for example, Uranus and Neptune are thought to be about 100 times solar metallicity. Saturn is hovering around 10 times solar, and Jupiter is a couple times solar. But there's only 4 planets on this plot. And so it is still not totally clear whether this is a universal outcome of planet formation or if this is just something that happened in the solar system. And exoplanets provide an opportunity to really broaden the sample. So one of my early results, this is from my PhD, was a measurement of the water abundance for a hot Jupiter. This planet is called WASP-43b. We observed its emission and transmission spectra with the Hubble Space Telescope using the Wide Field Camera 3 instrument. This is a near-infrared instrument that operates between 1 and 2 microns. It's very sensitive to absorption features from water. And as you can see in both of these spectra, we had very high confidence detections of water. And we ran an atmospheric retrieval. This is work from Mike Line to see what range of atmospheric compositions were consistent with the observed data. So we basically explored a range of chemical compositions and temperature pressure structures. And we found that based on the combination of all the data, we had to have a water volume mixing ratio between about 200 and 3,000 parts per million. And depending on who you talk to, that may sound impressive or may not. But for some context, this is a factor of about 100 improvement in precision over previous work. And more importantly, it allows us to put WASP-43b, this exoplanet, on the same scale as the solar system. And so it shows that this planet happens to follow the solar system trend really, really well. And that was actually a big surprise because because exoplanets, if nothing else, have surprised us every time we look at them in detail. But this was now about 7 years ago, if you fast forward to today, in fact, we do see that exoplanets have a huge variety of water abundances in their atmospheres. So that I think I was a little too naive maybe in thinking, oh, maybe the solar system is just totally representative. Not so. And one thing that is really interesting about the results that are coming out now is that many of these planets are best fit with models that have quite low water abundances, substellar water, and that is very challenging to achieve from a modeling standpoint. There's a lot of water in ice. If you're forming out beyond the water ice line and you accrete planetesimals, they bring water in with them, and you'd expect that to enrich these atmospheres. And so I think that I'd say the jury is still out. Like the data that we have at the moment are pretty limited. It's a fairly small wavelength range. A lot of the spectra are not that precise, but it seems like no matter how you slice it, whether you observe the atmospheres with Hubble at low resolution, or ground-based high-resolution spectroscopy, and fairly sophisticated models of the spectra that include effects from clouds and hazes, all signs keep pointing towards these low water abundances. So I think this will be something that's really interesting to keep exploring as our data get better. And I will show you a couple of ways starting now about the type of data we expect in the very near future.
Hey, Laura, before you move on,
yeah.
The subsolar water abundances,
Mm-hmm.
I mean, I know that everyone says that they're doing clouds and aerosols and everything properly, but like it's sorely tempting given that we don't really know how the heck a planet could end up so depleted in water. At least a big massive planet like this is very tempting to say that we're just completely bollocksing clouds. And in fact, all these planets have a lot more water than we think we're seeing in transit.
No, and I totally agree with you. And I put this slide in as kind of a provocation. Like I was hoping for exactly the reaction you gave. Because if you think about how the planets are forming, this is nuts. Like, where is the water? Like where is it going? Why can't we see it? Is something wrong with our models? And like, are we, is this a case where we have just models not fitting very well? And we're like, I don't know. It's getting to the point where I feel like I can't ignore it anymore. Because for a long time I was like, they just didn't do the clouds right. But even if you assume there could be patchy clouds, or you do a cloud and a haze, or you do a more physically motivated cloud with some kind of sedimentation deficiency, like it keeps coming up. So
okay, what about, so since in Zoom you're right next to Eve, how about another provocative question that maybe relates to Eve's area of expertise? Like what if these things formed closer to in situ than we like to imagine? So they didn't actually form beyond the snow line, and so they somehow built up a big rocky core, and then accreted a bunch of gas on top of it, and they never actually accreted much water. So that they actually are kind of dry in that sense. They've got a bunch of rock and a bunch of hydrogen and helium and not that much water. Is that possible? Would that explain this?
Substellar water though? Like it's so extreme.
Yeah, you're right. Substellar is hard. Yeah, you're right. That's still hard. Huh, weird.
Yeah, or maybe you can weigh in.
Just for clarification, is it subsolar or substellar?
These are generally solar metallicity stars, so you can they're equivalent. So you substellar.
Okay. I think this just gets into like just free discussion, so I don't want to dwell on it too much. But just I guess the one thing that I would, sorry, my computer is not working correctly. Sorry. I guess one thing that I would worry about is, so there is water content in the gas, and there's water content in the solids, right?
Mhm.
So I would be more cautious about like what is the relative fraction of the gas and the solids that you accrete at the location where these planets form. Because I could think of a scenario where you form outside the ice line, but that is all the water is locked into the solids and you never dredge it up all the way up to the point where you can actually observe. Like I can imagine it being dredging up like below, optical depth 1. That's fine, I can see that. But I think it's pretty hard to get it all the way up.
Yeah, I think, right. I mean, for some of these, I think this is a key point, that some of these hot Jupiters are so hot, like equilibrium temperature of 2000 Kelvin or something, that the general assumption has been that their atmospheres are well mixed. But yeah, if somehow all the solids just end up in the core and they're not in the atmosphere and they never get to the part that you see, maybe that explains why we're not seeing it. And yeah, and that's the other explanation that has been suggested, is that maybe if you form really far out, like beyond the all of the ice lines of the major volatile species, so water, CO, CO2, that you can get gas that is just really depleted in CN and O, and maybe that's why. And then somehow the planets had disk-free migration to get to their current locations. But that seems less plausible to me than just having all of your solids sequestered deep in the atmosphere in the core where you can't see them. Yeah, good question. I'm gonna, if it's okay, I'm gonna keep going. But I think this is a really, really interesting discussion. This is like one of the things that's been bothering me a lot lately, that we're sort of doing the best with the data we have and the models we have, and like again and again and again, the answer is coming back that the atmospheres are water poor. Okay, good. So let's talk a little bit about, and like my answer as an observer is always to say, like, let's just wait till we get better data. And maybe that will help shed some light on what's going on. And here is a direction for that I'm really excited about. This is a spectrum of a widely separated young gas giant, so a directly imaged planet, Beta Pictoris b, taken with the gravity instrument that was designed to observe actually the stars in the center of the Milky Way, but happens to be really good for exoplanets as well. So this is, and it's just because it's a K-band interferometer with tens of meters of baseline. And so you can spatially separate the star from the planet and get a really good spectrum. So here's an example for Beta Pictoris b. You can actually see the CO band head at 2.3 microns if you squint at it. And based on models of this spectrum, we were able to infer both the overall metallicity, which in this case was superstellar, so very different from most of the planets that have been studied in transmission spectroscopy, and also measure the carbon to oxygen ratio, and recovered a value of 0.43 plus or minus 0.05. And that is a really, really precise measurement compared to what we've been able to do for most transiting planets. And you can use this information to try to infer where in the accretion, where in the protoplanetary disk the solids were coming from. And so this isn't like a 3 sigma result, but I would say maybe a suggestion that to get a metallicity like this and a C to O ratio like this, the solids in the accretion process had to be coming from between the CO2 and the CO ice lines in the disk. Gravity is currently being upgraded, and I'm a co-I on the upgrade, which has been really fun. The sensitivity of the instrument will improve by a factor of 10, thanks to mainly better AO, a modern AO system for the VLT, and improved fringe tracking. And with data like this, I think, in principle, you can squeeze down the error bars on your model parameters. But I think that if we get a spectrum that looks like this, we'll be model limited in a way that we haven't been before. I think up till now, it's fair to say that we've been data limited. We've had noisy data, big error bars, systematics are sometimes dominating. But if we truly reach this level of precision, I think the complexity in our models will be the limiting factor in how well we can understand what the data are telling us. So this is expected by 2025 or so. We are also expecting exquisite spectra from JWST. This is a simulated spectrum of a hot Jupiter that is scheduled to be observed during cycle 1 as part of the Transiting Exoplanet Community Early Release Science Program. And this is an open program, so if you're interested in learning about how JWST works, learning about how you would measure planet spectra, this is definitely something that is open to the community. So if you're interested in getting involved, you can contact me. You can see from the simulated data that we expect to see spectral features not only from water, but a bunch of other species as well. So that could be methane, carbon monoxide, carbon dioxide. And with this complete spectral coverage between about 0.8 to 5 microns and really high precision measurements, we expect to be able to measure the atmospheric metallicity and C/O ratio really on a level that's on par with what has been possible for the solar system. And probably a lot of you know that something like 25% of JWST time during cycle 1 is going to exoplanets. So there will be a lot more science like this for a whole bunch. I think more than 20 targets will be observed in total just in the first year. Later down the line, we have the Ariel space mission. This was recently selected by ESA for launch in the late 2020s. And this is going to be the first space mission that is dedicated to exoplanet atmosphere characterization. And I think Ariel is going to be really important because we'll build up a statistical view of what these atmospheres tend to look like, predominantly gas giants. But exoplanet atmospheres are so complicated that I think even if we have really exquisite measurements for a small sample, there are so many different factors that are important, everything from the temperature of the planet to its underlying atmospheric composition, its rotation rate, what type of star it has, the UV spectrum of the star, all this stuff. Even with a sample of tens of planets with spectacular spectra, it's not going to cut it. And so the goal of the Ariel mission is to survey over 500 exoplanet atmospheres systematically to build up a library of spectra so that we can understand planets as a population rather than on a case-by-case basis. And finally, rounding out the decade, it's going to be a really exciting 10 years or so for exoplanets. There will also be really fantastic new capability coming from the ELT. This is a simulated spectrum of a hot Jupiter from 10 hours of METIS observations. And the stellar spectrum is removed. So what you're seeing here is an actual exoplanet spectrum at high resolution. You can see the shapes of the spectral lines. And if you push to this really, really high spectral resolution, it enables you to detect additional chemical species that have that are less spectrally active and might be swamped by absorption lines of the dominant absorbers, usually water. So you can use this to detect isotopologues, for example. And in fact, that's already been done for a brown dwarf. And by measuring the shape of the line, it's also possible to constrain the wind speed and the atmospheric dynamics. With precision like this, we'll even be able to map out how the chemical composition and the wind speed is changing in different regions of the planet's atmosphere. So you could look at like the red shifted part of the spectrum and tell the composition of that half of the terminator region. And you could also look at the blue shifted part and compare the two to really turn the planets into the true 3D objects that they are. Okay, so that is a whole bunch of hot Jupiter stuff. I want to switch gears now and talk a little bit about smaller planets that are more like our own Earth. And there we hear a lot about Earth twins. We're still a long way away from actually being able to characterize the atmospheres of Earth twins. So I want to bring us back a little bit to a slightly easier question, which is Earth cousins. And by that, I mean planets that are a little bit bigger or a little bit hotter than the Earth. So planets a little bit bigger than the Earth, I'm talking about this intermediate population that is in between the Earth and Neptune in size. These are roughly 2 to 4 Earth radii. I'm calling these Neptini because I think sub-Neptune is really boring. And also because they're probably more like Neptune than they are like Earth. Based on interior structure models of these planets, we'd expect them to have at least some hydrogen in their envelopes, though the atmospheres might be highly enriched in volatile species like water or methane. And I should note that that's coming from models. That's not something that we have been able to determine yet based on measurements of masses and radii alone. Okay, so here's an old friend of mine. I think this was mentioned in the introduction. This is the transmission spectrum of GJ1214b. It is a canonical Neptino. It's about 2.7 times the radius of the Earth, 550 Kelvin, orbiting a small nearby star. It is more observable than, thanks to its small, bright host star, than any other known planet in this size range. And so we decided to go big or go home and observe a very, very precise transmission spectrum of the planet with Hubble. And this is what we found. This has been called the most famous flat line in astronomy, but it's a very informative flat line. So you can get a featureless transmission spectrum if you put clouds or haze high up in your atmosphere. They tend to truncate the amplitude of spectral features roughly at the altitude of the clouds or the hazes. And indeed, this is the constraints we got on where the clouds need to be, a lot higher up than Earth clouds, so roughly 1/10 of a millibar in pressure. At the temperatures on the planet, you could get salt and sulfide clouds, or you could also get photochemical haze formation that is the result of methane photolysis. If you zap a methane molecule with a UV photon, it can break up and then recombine into these higher order hydrocarbons, similar to what we see on Titan. This is just for fun. This is what the actual color of GJ1214b might look like. These are some models from Ben Charnay that he convolved with the human eye response. Assuming that the planet was illuminated by a red dwarf, that's the top row, or the actual sun, that's the bottom row. Pretty much no matter what the atmosphere has going on, the planet is kind of an ugly color. I was a little disappointed by that. But if that's what nature gives us, that's what nature gives us. So if you're ever asked by the press or your friends or something, what color are these planets? You can say it's kind of like a sewer green or brown. So this is a really important point, that not all of these small planets have clouds. This is something that comes up a lot in observing proposals. You discover an exciting new planet and you go ask for time to measure its spectrum, and the review panel comes back and they say, oh, but what if it's cloudy? First of all, if it's cloudy, that's interesting to know. Second, they are not all cloudy. And here's a very tentative trend that I identified in a paper with Ian Crossfield a couple years ago, where we looked for any kind of physical parameters of these planets that might explain why some are cloudier than others. And we found from our sample of 6 that there is a tentative increase in the amplitude of spectral features with temperature. And that could be related to the fact that there are fewer species that are condensing at these higher temperatures. Or maybe there's a break point around 800 to 900 Kelvin where methane is no longer chemically favored. And so you wouldn't expect these photochemical hazes to be forming. But point is, we saw very tentative evidence that hotter planets tend to have less cloudy atmospheres. Since that time, we've had some really exciting new results. Probably most of you know this one. This is the transmission spectrum of K218b. This planet is about 2.5 times the radius of the Earth, but what makes it really special is that it's in the habitable zone of its host star. And it has a very, very nice spectral feature detected in data from Hubble. And that came as a surprise because this is the coldest planet of all that has been studied with Hubble in detail. And so if you followed the previous trend, this one, you'd expect it to be even cloudier than all these other ones. But instead, we see the opposite, that it has some of the largest spectral feature of any subneptune that has been well characterized. So why is this? I think we don't know yet, but a really interesting idea just came from Xinting Yu in a paper that was published in Nature Astronomy a couple of weeks ago. And she did lab experiments studying the surface energy of hazes that are produced when you put gas in a chamber and you shine UV light into it, it makes hazes, and then you can study the properties of the hazes in the actual lab. And depending on the surface energy of the particles, the haze properties vary a lot. So if you have high surface energy particles, that tends to favor coagulation. So the particles will grow and get heavy and rain out of the atmosphere, whereas low surface energy particles don't stick to each other and they linger up high. And it appears to be a sweet spot for high altitude small haze particles in the 400 to 500 Kelvin range, not so far away from the famous cloudy planet GJ1214b. But as you move to cooler temperatures, including the habitable zone, the surface energy of the particles gets higher, so those hazes can rain out of the upper atmosphere, and we can actually look and see a cloud and haze-free spectrum and determine what the composition of the atmosphere is. So that's a really exciting brand new result. Okay. I want to switch gears now and talk about a different type of Earth cousin. And this is planets that are the same size as the Earth, but a little bit hotter. And so why are we interested in these hot planets? Simply because they are easy to study, or easier to study right now. And we have a very limited sample in the solar system. And so if you're interested in this very 0th order question, where do atmospheres survive, under what conditions, what temperature of planets, this provides an opportunity to address that in the near future. So in the solar system, we have 4 rocky planets: Mercury, Venus, Earth, and Mars. 2 of them have maintained thick atmospheres, that's Venus and Earth. 2 of them have not. So 50-50 chance. We also know that most of the rocky planets in the galaxy orbit smaller stars, which might have very different conditions for the planets that are orbiting around them. So M-dwarf planets are kind of a blessing and a curse. Thanks to the small size of their host stars, they're relatively easy to study, but their atmospheres are in some danger. So M-dwarfs are relatively bright in the ultraviolet. They can be more active, and both of those things can contribute to substantial atmospheric loss over the lifetime of the planet. Furthermore, the habitable zone around an M-dwarf is much closer than it is to the sun, physically closer. And that means that the planets, even habitable zone planets, may be tidally locked, which can lead to atmospheric collapse on the cold night side. And so this isn't like a game over problem. Like if you put an ocean on the planet that can help with this, you might be able to reinflate your atmosphere if you have late stage outgassing that happens after the star leaves the really bright pre-main sequence phase where it's blasting the planet with UV radiation. But point is, we have got to go and actually test this for real. We know of a lot of nearby M-dwarf planets. And my job as an observer is to go look at those and try to figure out, just to begin with, do they have an atmosphere or not? The nearby rocky M-dwarf planets have been studied in quite a bit of detail. For a number of these, there are high precision transmission spectra measured from space that rule out cloud-free, hydrogen-rich atmospheric compositions. So that's most of the TRAPPIST planets, as well as GJ1132b. But we didn't really think they would have hydrogen-rich atmospheres to begin with. You have to have a very finely tuned amount of hydrogen that can easily escape. But based on the existing data, high mean molecular weight atmospheres are possible, clouds are possible, and there's also a possibility that there's no atmosphere there at all. So how can we tell whether an atmosphere exists? There's another way, which is to observe a thermal phase curve of the planet. And the idea here is that thin atmospheres are really bad at circulating heat. So for a tidally locked planet, the larger the temperature difference is between the day side and the night side, the thinner the atmosphere has to be. Whereas if you have a thick atmosphere, it helps homogenize the temperature over the entire surface of the planet. This planet, LHS 3844b, is my current favorite. It is the first terrestrial, so truly rocky planet that was accessible for this type of phase curve observation. In a lot of ways, it's really representative of the class of small planets around small stars. So it's about 30% larger than the Earth, orbiting an M-dwarf at 15 parsecs. What is special about it is that it has a very short orbital period, just 11 hours. And that means that the equilibrium temperature of the planet is about 1,000 Kelvin, which is hot enough to be detectable potentially, but not so hot that any atmosphere would be gone. So if you put a Venus-like atmosphere on the planet, you'd expect that to be stable over the lifetime of the system. So this is one of the very first test discoveries. I was crawling through the list of candidates and I saw this one, got really excited about it, and wrote another go big or go home proposal. This was 100 hours of Spitzer DDT time in the last 6 months of Spitzer's operations to observe 9 orbits of the planet at 4.5 microns. Here it is. I've talked about this a lot, so many of you probably heard me getting excited about this at other talks, other conferences, but here it is. This is the data. You can see very, very clearly right away, there's a large amplitude phase variation, so much hotter on the day side than it is on the night side. You'll also note that there's no apparent offset in brightness from the substellar point. So this is a symmetric phase curve centered at orbital phase 0.5. The temperature of the night side is consistent with 0. The temperature of the day side is about as hot as it could possibly be. So all of this is pretty bad news for the existence of an atmosphere on the planet. But I wanted to do my homework and see exactly what types of atmospheres we could rule in or rule out. So I put together a dream team of theoretical modelers. This is some really awesome work from Daniel Cole and Caroline Morley, considering a range of plausible atmospheric compositions. So no water. We think that the the water would have photodissociated a long time ago and maybe left over some oxygen. Likewise, CO2 is hard to get rid of. So these are oxygen and CO2 mixtures. We found that regardless of the atmospheric composition, we could rule out thick atmospheres with a surface pressure greater than 10 bars. For a Venus-like atmosphere with a essentially 100% CO2 composition, we can rule out much, much lower surface pressures down to about 0.1 bar, and that's because CO2 has an absorption feature at 4.5 microns. We also did some modeling of how much atmosphere can survive on the planet, and we found that it's fairly easy to erode an atmosphere with a surface pressure of 1 to 10 bars over the lifetime of the planet. So thick atmosphere, punchline is thick atmospheres are ruled out. Thin atmospheres easily escape to space. And so most likely what we're looking at is the surface of a rocky exoplanet for the first time, which is really cool. So of course we want to know what kind of rock might it be. And these are a couple of different rock surface spectra from Renyu-Hu. And you can see that they look different. To first order, granite, for example, is higher albedo than some of these other than like a basaltic composition, which would be very dark, for example. And the fact that we measured such a high dayside temperature for the planet means that it has to be a highly absorptive surface. So we found that the best fit compositions are basaltic in nature, which is similar to the lunar mare or the surface of Mercury. You can get this from cooling lava. So perhaps the planet had a magma ocean early in its history that has cooled off to what we're observing today. We expect to see really, really big progress with James Webb on the atmospheres of rocky planets. There's already a bunch in the queue for cycle 1. And we're not going to do biosignatures with James Webb. In my opinion, I don't think we can do this. But I think we will learn a lot about how often and what conditions rocky planets can keep atmospheres. And if there is an atmosphere present, for the best, highest signal to noise cases, we'll probably be able to detect spectral features from the dominant chemical species. So here's a simulated emission spectrum from a paper led by Caroline Morley for, I think this was GJ1132b, for a simulated emission spectrum from MIRI. And you can see that not only can you detect the planet's atmosphere, but you can also start to distinguish between chemical compositions dominated by water or by methane or CO2 or something else. Okay, I know we're at the end here, so this is my last slide. I talked at the very beginning about biosignatures and the search for life being a really big motivator for the science that we do, and then I haven't come back to it until now. And that is because it is extremely difficult to measure the spectra of truly Earth-like planets well enough to find evidence for life. The canonical biosignature on the Earth is the simultaneous presence of oxygen and methane. That's not the only possible biosignature, but that is definitely what would make Earth stand out if we were aliens looking at it from afar. And the main idea is that the atmosphere is out of equilibrium, that you wouldn't expect both oxygen and methane to be there in the abundance that we have without some source that is producing those constantly, and that there's no plausible explanation besides the presence of life on the planet to produce oxygen and methane as we see them on Earth. To detect an equivalent biosignature on a statistical sample of exoplanets, so not just 1 or 2 or 3, but tens of planets, the best way to do that is with a next generation space telescope. So this is beyond JWST. I know that we are all anxiously awaiting the results of the 2020 decadal review. Hopefully that will be coming out any day now. There were a lot of different missions that have been discussed, LUVOIR and HABEX in the United States, the LIFE mission in Europe. But this is something that this is the biggest question we can answer. And so even if it takes 10, 20, 30 years to address it, that's something that I think we should absolutely do. So I'll stop there, and I'm happy to take a couple questions in the few minutes we have left.
All right, thanks, Laura, and I'll clap for everyone else because we're doing this virtually. All right, question.
I'll stop my share so I can see faces.
I see a question in the chat. Trung, did you want to speak? Did you want to speak up, or would you like me to read it out? I'll just read it. Okay. In an extrasolar system, if the equivalent of a Kuiper belt exists, how does it affect the water signature in your planet atmosphere measurements?
Oh, that's a good question. So usually for a transiting planet, we're making a differential measurement so that we can directly compare what the system looks like when the planet is in front of the star versus when it's not. And that's the trick that we use to make certain that the signature we're seeing is from the planet and not something else. So the short answer is we wouldn't, if there were some other water absorber that were present, we wouldn't see that as a false positive because it would be there all the time, whereas the planet is moving around. Good question. Yeah.
All right. Other questions?
There are no bad questions. So if you're shy, don't worry. I see Nick.
Yeah, so I have like a really naive question about the gravity thing. So is this the same gravity that experiment that people use for studying like the galactic center and stuff like that? Okay. And what, so in the exoplanet context, it's a direct imaging type thing, like you're doing direct imaging, like it's sort of like high contrast imaging, but is there like a coronagraph? I'm just trying to understand what sort of planets I should get excited about using this on.
Right, so it's going to be this similar population as direct imaging. It's like the main idea is that rather than using a coronagraph to suppress the starlight, you use spatial separation. The inner working angle is smaller than any coronagraph pre-ELT, thanks to the long baseline. And so we think that if there are like Jupiter analogs discovered by Gaia, we could go find them. The challenge with gravity is that it has a really small field of view, so you can't use it to efficiently search for stuff. But if you have radial velocity or if you have astrometry and that helps you point put your fiber in the right place on the sky, then you might be able to see it. And so we think that we could get maybe like 10 to 20 planets where there's Gaia astrometry, where we could have a mass and then also measure the luminosity. So we've got both of those.
So is that a similar population of planets to what like the Roman Space Telescope is going to directly image-ish? Like also going after
No, so Roman is in the optical and this is in the K-band. And so we're most sensitive to young things that are still hot.
Oh, I see.
Roman, yeah, whereas Roman would have the reflected light. Yeah.
Okay.
Yeah, good question.
All right, so I think we're at the hour. And it's near bedtime, I think, on Laura's side. So thanks again for the really great talk.
Thank
and
you.
I'll clap.